First of all, I wish to thank the organizers of this session for inviting me and sharing our experiences with the participants of the EXplORE program. In our first contribution today, we want to talk to you about exploration targeting, strategies and technologies for exploration targeting, and discuss with you some examples from Germany and various foreign countries. So first of all, we need to discuss the question, what is an exploration target? The definition of a target depends first of all of the scale and level of investigation and the intended use of the target. In the next slides, I wish to discuss with you some of what can be a target. So it can be a larger area, it can be a new occurrence in a known mineral belt, it can be a mineral deposit by itself, or even a new ore body in a known deposit. On this photograph here, we can see an artisanal miner in Namibia digging for amethysts. So these little amethyst crystals are now his exploration target. Those are another two examples of exploration targets. In Tanzania, at the top photograph, we can see is a huge Buswagi gold mine owned by Freiberg. The ore body here has a thickness of around 30 to 50 meters with an average grade of 3.4 grams per ton. It's marked here by these blackish colors and is dipping steeply down. The end is open. Here another type of target, a narrow quartz shear zone, bearing gold, close to the village of Mafalungu, mined by small-scale miners in Tanzania as well. And here another target of a huge size, Salario Uni, the probably biggest lithium target or lithium resource in the world. So targets may change over time. They depend on the frame conditions determined by economy, infrastructure, political environment, economic environment, market conditions, etc. What we can see here on this slide is a Google Earth image from Ghana, the famous Ashanti Belt. And what we can see here are valleys. Valleys mined out completely. So all these valleys have been affected by gold mining, artisanal gold mining. Here, these, and even the smaller valleys. By very simple technologies mostly. The indication whether it's economic or not is a rule saying 3 gold specks on a shovel show an economic grade. So here we have environmental damages, enormous environmental damages, but the mining is easy. The targets are clear valleys and they are easy to identify. Here another example of a target. This is the Chem mine in Tanzania. It's a Lupa goldfield. It's a vertical vein-like structure with an extension of more than 1 kilometer, a thickness of 1 to 2 meters, as the surface completely oxidized. The grade is not clear, but it is probably high, more than 10 or 20 grams per ton. It is mined by the local people by hand picking, hand washing, and use of mercury. And what we can see here is a construction of a mine. The vein actually is striking here, dipping vertical down, and the Chinese owner of that license decided to construct the mine without drilling without resources, without methodology, and without feasibility. So now we go to Mongolia. Another gold target, a quartz vein with a thickness of around 1 meter. The known striking extension is more than 50 meters. It's composed mainly of milky white quartz and black tourmaline, and the potential size is around 200 by 100 by 1 meter. The wall rocks are slightly altered, but the mineralization is limited strictly to the vein itself. The grade is around 2 to 4 grams. So we have a potential resource of 160 kilograms. Some more lenses are expected nearby, distances of some 100 meters up to kilometers. The mining conditions would be a small underground mining. But this here is something different. This is a granodiorite, but what we can see here below is a so-called metasomatite, an altered granodiorite bearing bigger gold ore bodies in the nearby Boro gold deposit discovered in the 80s of the last centuries. The thickness here is unknown. The known striking extension is 20 meters as observed at the surface, but it could be huge. So the potential is exceptional. Assuming an average grade between 1 and 10 grams per ton, we may have here tons of gold in this potential ore body. The mining conditions would be excellent by a larger scale open pit mine. So what we can see on this slide is a Google Earth image taken some years ago from exploration drilling on this gold deposit, Boro gold deposit in northern Mongolia. What we can see here are the drilling points in a grid 40 by 40 meters, targeting an ore body stretching more or less horizontal over distances of kilometers, but hidden in this mountain here. It was explored first by the East German geologists and Mongolian geologists in the 70s and 80s, followed up by Centerra Gold Mining, a Canadian company. The total reserves here were 60 ton. It's now completely mined out after 10 years of mining. So this is how the Mongolian landscape looks like. It's almost covered. You can't see anything. A loose cover is covering it. The thickness is between 30, 40, 50 meters up to maybe 1-2 meters. But outcrops are very, very certain. So those are maps produced by Centerra Gold showing the horizontal projection of these ore bodies. What we can see is the scale. We can see the scale is up to 5 kilometers. No? And the section shows how these ore bodies are located, stretching like carpets. So very easy mining, very good mining conditions. Very good thicknesses in an acceptable grade of around 3 grams per ton. A very good target compared with these quartz veins. Now the question how we can find more targets around the known Boro gold deposit. Usually people use placers. So we have here the Boro hard rock gold deposit and placers around it. So the placers would probably guide a geologist to the hard rock gold deposits, the placers or stream sediments. So we have here more hard rock deposits, known deposits. We have here more placers, and probably this placer may guide geologists to another hard rock deposit. What was then identified here, the Katsurt, completely different type, a vertical ore body related to this large Zugchikte fault zone. But if you think that always placers or stream sediments may guide geologists to hard rock gold deposits, it is wrong, because what we can see here, we have low-grade Jurassic gold-bearing conglomerates producing placers by themselves, recent placers. And so these placers here guide the geologist to the Jurassic conglomerates, which are by themselves not economic because the gold grade is too low in them. Further, a word about placers. This is a typical Mongolian landscape. We can see here a flat slope, the recent valley, a steep slope with some hard rocks outcropping, and again the loess cover. Now, if you look for placers, where they could be, are they here in the recent valley, or more maybe below these slopes? So the valley has been shifted from the center here because of a block movement. So the block is a bit inclined now. And if you look below, the geology below, we can see the old valley is much, much deeper. This is around maybe 20 million years old. And the placer, the biggest placer is here at the bottom of the old valley in the center between the tops of the mountain ridges below the flat slope. And in the recent valley, we will find only a very, very modest gold placer, not worth to be mined. So geomorphology is very, very important when we look for placers. We now return to Ghana. Much placer gold, but here the geomorphology and the geological history is completely different. The terrain was elevated, and the oldest placers are located on top of the flat hills. So with this placer here, the old terrace placer, probably 20, 30 million years old, located around 40 meters above the recent placers. And this one is located around 10 meters above the recent valleys. As we can see from their brownish color, they are with laterite, so they can be clearly distinguished from the whitish, grayish recent placers. So the oldest placer here is on top, and the youngest is in the big valleys. Now the big question is how to locate these placers here on top. And this is a question we may discuss a bit later. But as the gold has been accumulated from this placer to this placer and from this placer to this placer, the best placer might be the youngest one. And here the best placer is the oldest one. So now a few words about the theory, the approach, the steps of prospecting and exploration according to the United Nations Framework Classification of Mineral Resources. We have three different axes on how to evaluate the value of a mineral occurrence. So we have the axis of geological knowledge, reconnaissance, prospecting, general exploration, detailed exploration. This informs us about the situation, the geology of the deposits, the grades, etc. Then we have the feasibility axis. This axis, or this knowledge, informs us on how the mineral can be extracted from the ore, what the technology is about. And then we have the economic scale or axis informing us whether the deposit can be mined with profit or not. In many cases, people are just mining, so they are here and they don't do really exploration or the investigation of the technology. But in this case, the resource is mineable because the mine will sustain itself. If you bring it down to a flat spreadsheet, we have here the geological knowledge, we have here the feasibility studies or knowledge, and we have here the mining status. Means those are the mineable resources. And here's some more explanations from the Canadian standard. A mineral resource is defined as a concentration or a source or occurrence of minerals in such form and quantity and of such a grade or quality that it has reasonable prospects for economic extraction. There are three different types of resources: inferred, indicated, measured. You can read it by yourself later, of course. So reserves or higher class reserves are the economically mineable parts of measured or indicated mineral resources, demonstrated at least by a preliminary feasibility studies. So we have proven resources and we have probability resources. So it's also higher class. And another chart indicating this, so we have the resources, we have the reserves, and we come from indicated to probability to proven. So, but now back to praxis. Eastern Africa, prospecting for minerals in Eastern Africa. Tanzania, DR Congo with its huge copper resources, and tin, tantalum, and tungsten in Rwanda. So the geological situation is here. East Africa is the Tanzanian craton, the famous Kibera belt, famous for its gold deposits, and tin, tantalum deposits here in Rwanda, Tanzania, Burundi, and the Lufilian arc stretching from DRC to Zambia with its huge copper deposits. So Rwanda, a very, very small country in Eastern Africa, but famous for its tin and tungsten deposits, and tantalum, of course. So we had the pleasure to work for the Mineral Authority of Rwanda several years ago, and we are now presenting you some outcomes of these investigations. This is the landscape in Rwanda. It's mountainous, it's a tropical wet environment with a huge laterite cover, up to 60 meter meters of oxidation zones. So we have to adjust our strategy to this environment. Stream sediments are a good idea in these mountainous areas. So mineral occurrences or outcropping mineral occurrences are exposed. We can use stream sediments to locate the anomalies, to locate the outcrops, but then undercover we need to trace them by different technologies. This here is an example for pegmatite mining. So we have these pegmatite veins in the Kebaran schists. As we can see here, this is the pegmatite, but the pegmatite is mined here only in these adits. So this is ore as well. What we can see here is a waste of mineral, of course. So the approach here is a combination of methods, geology, geochemistry, geophysics, and data processing. We started with stream sediment sampling, followed up by soil sampling, and then followed up by pitting and drenching, accompanied by hard rock sampling, geological mapping, and ground geophysics. These areas have been predefined by the Geological Survey Authority of Rwanda for further detailed investigation. What we see here is a stream sediment map of tantalum. So we can see high-grade anomalies and many low-grade tantalum geochemical field. This sketch shows you the general picture. We have these Kebaran schists, we have granites, and we have pegmatites, and the thick laterite cover in flatter areas. And the mines are located here at the steep valleys where the pegmatites are outcropping. But it's very hard to identify these pegmatites here. So in field work, we usually have our tablet computers combining a GPS, a camera, the notebook, and the data capture forms. The hammer, of course, we need a separate hammer. But these tablets are very useful because they have a good GIS functionality and the data capture spreadsheet in them. So we can upload any kind of pre-existing information like topographic maps or remote sensing data, and the tablet shows you where you are, and then you can open the spreadsheet and type in your observations. So here, this is the first step of data processing of geochemical data. We transfer the sampling points to the catchment areas and color the catchment areas by the grade of the metal. Here's a tantalum map. So what we see here in this chart is a niobium tantalum chart. Usually in normal rocks, the relation of niobium to tantalum is 20:1, but in these pegmatites is 1:1. So this relationship here, ratio, indicates normal rocks, and here this indicates the pegmatites and also a tantalum grade of more than 6 ppm in stream sediments indicates the presence of tantalum pegmatites. Those are experiences, but this is a geochemical consideration. So now, in this area, we decided to follow up the stream sediment activities by soil sampling in a grid 100 by 25 meters. So the grades are increasing here, we can see, and they allow somehow to shape already possible outcrops of pegmatites. Here we can see known pegmatite mines already in our photograph. Now, somehow we need to estimate the possible resources. So we have, for instance, here an area of 53 square kilometers with a grade of more than 6 ppm of tantalum. And around 50% of this stream sediment anomaly here are occupied by a soil sediment anomaly, soil anomaly with more than 6 ppm. The experiences show that 5% of the soil anomaly are underlined by pegmatites. So 2.5% of the total area of the stream sediment anomaly then are underlined by pegmatites. From the pegmatite sampling itself, we have the average grades of the pegmatites. A grade, if we assume a cutoff of 60 ppm, the average grade is around 200 ppm. So we can assume 1.25% of the stream sediment anomaly carry all pegmatites with a grade of 193 ppm, and assuming a density of 2.6, we may roughly calculate a potential of 7,000 tons of contained tantalum, and considering the losses of 1.7 kilotons of tantalum, assuming a mining depth of 20 meters. But this, of course, are very, very rough estimates, but they give us a chance to evaluate and rank the targets. A few words about geophysics. What we see here is a conductivity map. We tried to trace these pegmatites here by a conductivity survey, but as we can see, it doesn't show much. So in case of these pegmatites, the geophysical ground survey is not really helpful. Back to the pegmatites. How to trace them under thick laterite cover. So back to this chart, we have here normal rocks with a ratio of 1:20, tantal to niobium, and we have here a few points indicating rare metal pegmatites with a ratio of 1:1, and this indicates a mix of sources. So how do you identify possible pegmatite outcrops here? So those are the known mines related to the valleys. So here are the valleys with the known pegmatite mines, but here where we can probably find pegmatites is these flat mountain tops. The mean is here soil profiles. This is the profile here. Already the results. We can see here the tantalum niobium ratio from the background grade of 0.05, 1 to 20, having here maximum values up to 0.25, the ratio. And this is the absolute grade of tantalum in soil and niobium in soil, tin in soil. If we have a closer look at these profiles, we have here the tantalum grade and the ratio niobium to tantalum. And we have here a chart helping us to identify the amount of the possible pegmatite underlying this type of anomaly. Means if we have here a ratio of 1 to 4, we can assume that 25% of this interval of 25 meter sampling is underlined, or 50 meters underlined by the pegmatite, or 12.5 meters as a very, very rough estimate. And this helps us now to outline the possible ore bodies to be followed up when by drilling. So we have here the recommended extension of the soil profiles and points for drilling shown on this map here. The final results of the geochemical and geological investigations are shown on this map. We called it map of mineral potential indicators. Another very, very important issue is are the losses. We already discussed it. It's also important when evaluating a target. No? So we have here, we can see here huge mining losses and also losses, metallurgical losses. So this is all tantalite. So the grade in some of these sediment samples below the processing plants rises up to 900 ppm tantalum. It's almost 0.1% in this silt here. And remember, the grade in the ore itself is around 200 ppm only. So, but now about another mineral, tungsten. But before I want to come to issue of data processing. Till now, we have only made a very, very simple data processing using just the absolute values of the elements or the ratios of the elements to evaluate targets. Here we have now more advanced possibilities, statistical methods and neural networks. Neural networks is a kind of artificial intelligence. So we are processing our stream sediment data. We relate what we already did, the sampling points to the catchment areas. Then we grid the data. We logarithmic them and create these anomaly maps, which we use as input data sets to feed them into the statistical data analysis, here like factor analysis or the neural networks. The simpler analysis is here a factor analysis. So we put the 40 element grids in and let the software work, and then the software identifies groups of elements which somehow belong together, and then we try to relate them to the practice, to the true, what they may tell us. So we have here the first factor, rare earth elements. The second factor is a cobalt, copper, iron factor. The third one is hard to interpret, and the fourth one indicates the pegmatites with tin, tantalum, beryllium, and lithium. So then, returning to the maps, we create these maps with the factors, the rare earth factor, the copper cobalt factor, indicating this belt here, for instance, and this here. But then if you compare it with the artificial neural network, we see the neural networks are much sharper, but they require training data. This scheme shows you how to process data, geological data, geochemical data in this artificial neural network environment. We have training data, means known mineral occurrences, and we have our data, geochemical data, geophysical data, etc. We have a certain understanding of what we are looking for, and using this understanding, the exploration model, we're extracting from the primary data the model input data. We'll discuss it a bit later, after tomorrow, and then we create this target map. And what we can see here is a target map created by these neural networks, and we can see how sharp it is compared with the map created by the factor analysis. The details of the neural network-based data analysis we'll discuss after tomorrow. So now a few words about tungsten. Tungsten is another mineral of Rwanda. We can see here these bigger tungsten anomalies, but now the question is, where are the mineral deposits or occurrences? So here is one of these anomalies. Here is a soil profile, here's a mine, and here's another mine. We can see a very shallow soil anomaly in this soil profile, crossing these tungsten-bearing quartz veins. So the height, the level of the anomaly is very low. It's just 13 ppm compared to a background value of about 5 to 6 ppm, because the tungsten mineral wolframite is not stable at the surface, is going oxidized, and the tungsten is washed away. So this is how the mineral occurrence looks like. It's mostly quartz veins with scattered big tungsten crystals, wolframite crystals, that are hand-picked out of the ore. So these mines produce a very high concentrate, but the productivity is not much, of course. It's just some 20, 30 tons. And we do not have reliable grade information about these veins, but it's probably not much. It's just maybe a 200 ppm in the vein. And here we have a similar problem. Because of the metallurgy, we have huge losses. So much of the tungsten is washed away. So we have now the target maps. So for the tungsten, we cannot recommend drilling yet. We first need to have these soil profiles before we can recommend drilling. But here in the pegmatite area, we already identified some drilling points and recommended them for follow-up work. Related to the bigger picture, we can see that probably tungsten mines known in this part of the country, or tungsten deposits known from this part of the country, those are known deposits, stretch further in these metallogenic belts. Yeah, this is an image or picture showing the processing of the tungsten ores. Very, very simple technology. So, but now if we compare the general value of the mineral possible or potential mineral occurrences related to the mining technology and the target of the country to bring people into jobs to develop the economy, we can see that clearly tin and tantalum have the best, highest potential to be developed. Gold we didn't discuss, but we have only a few low-grade gold deposits or occurrences in the country. So this is more or less simple mining, can be done by small-scale mining. For tungsten, we already need a bigger underground mine. This is a medium-scale mining. So this probably has the highest potential for the country to be developed. A few words about the Kathanga Belt. This is a project we were working on behalf of the respective ministry of the Democratic Republic of Congo 2 years ago. The famous Ophidian arc, southeast of Congo, in between Congo and Zambia. So the geology is marked by these Kathanga rocks. We have here the Kibara rocks stretching from Congo up to Rwanda, where we have been till now. We have many mining companies working here. The biggest copper mines of the world and the biggest cobalt mines of the world are located here in these areas. And the question was whether there are more discoveries possible, especially where occurrences do not outcrop. So we have 3 types of copper deposits. Knuckle related means they are thrusted, over-thrusted, and this is a remnant of an outer thrust. In a different geological environment, the copper occurrences crop out. Those mines have been found many years ago, exploited by the local people, and then over the last 120 years mainly by foreign companies. Another type is thrust related. They also crop out, but they are very narrow, having a long stretching along these thrust faults, but outcropping. This is an example of a mine mined decades ago, and now underwent a new exploration targeting the follow-up of the ore bodies along these thrust faults. But then we have big areas looking like this, flat, covered with Kalahari sands, no outcrops, or covered by a soft soil cover. And here, 2 big copper mines have been identified in the last year, probably the biggest copper resource in the world, called Kamoa and Kakula. And the question was whether we can identify possible targets like this in the bigger area, but there are no outcrops. So we are talking about these areas here, Kathanga units, yes. So what do we have? We have these thrust faults. We have a simplified geology, this one, telling us about the general prospectivity, Kathanga. Then we have the thrust faults. We have airborne geophysical data, radiometrics, and magnetics, and we have geochemical data, surface geochemical data, similar to what we have shown you already. We relate the sampling points to the catchment areas and then create gridded data covering the entire area. So we did some preliminary exploration targeting, went to the field and checked the positive indications and verified the target modules, the neural networks, and then created the final neural network grid, helping us to create these final prospectivity maps. So, and this is an example of the final maps showing us the target type 2 along these thrust faults, where probably the mineralization crops out undercover. A few words about the discovery of something very unexpected. The Erzgebirge of Germany, a very interesting brownfield area, mined for 800 years, having a size of around 5,000 square kilometers, and famous for tin, uranium, and silver, and many more metals mined over the time, like copper, iron, tungsten, etc. So this is an exploration model of tin in the Erzgebirge as a summary of many pre-existing exploration models created over the last decades by different researchers. But the conclusion here is tin belongs to granites. Either related to veins on top of the granites, or related to crescents in the top of the granites, or related to subvolcanic bodies in the granites and in the schist environment, or here in this rhyolitic environment, the big caldera of the Eastern Erzgebirge. And here we have the skarns, where granites cut carbonate rocks. Big tin-bearing skarns have been formed. But now, a new geochemical survey we identified low-grade tin anomalies of 25 to 40, 50 ppm of tin. They have never been traced in the past because people were focused on the high-grade tin anomalies with the many known deposits. And a few years ago, we identified tin in phyllites, means metasediments, with grades that are not bad. You can see here a measurement up to 1% grade in a thin layer in this phyllite. But it is somehow against the rules. It is not related to a granite. We don't know what it is. It's not clear what the extension is, the metallurgy, the mineralogy, if there are more of this type of tin or not. And we need to understand what it is. About this we will talk more tomorrow. But what we can see here in this last slide is a big concealed granite we modeled using magnetic and gravimetric data under this belt of the low-grade tin anomaly. So now we probably come to the end of the first part of this lecture. To summarize about exploration targeting and exploration target evaluation. Very important here is to understand that the projects are different. The minerals are different, the mineralization types are different, and the targets are different. And there are universal approaches, and the universal approaches are: we go from general to details, we go from surface to depth, we go from known to the unknown, we go from cheap to expensive methods. But the survey strategies and technologies must be well adjusted to the targets and to the geological and natural environment. And we must be unconventional, and we must consider something unexpected, which we don't know, which does not fit into our exploration models. And we always need exit strategies. If we somehow feel that we do not find something reliable, it's better to stop at a certain level. So we always need to consider the financial aspects of our work. So thank you very much.